Thanks, Lars. Yes, and I've only been here for half of the winter, so I only half understand how awesome the winter is here compared to the East Coast. So first of all, let me thank all of you for coming. This is great. It's a great opportunity to talk about some scientific areas of study that I think are incredibly interesting and really fundamental. And KITP is a great place. To do this, and it's really great to have all these programs and see all these people. And we just had a short program on dark matter, and it was really lively. And this room at the end of it was packed to the rafters, waiting for new results from some experiments. And it's just been really, it's been a really fun time since I've been here, and I've only been here a few months. Okay, so as I said, today I'm going to talk about dark matter. It is a fundamental topic, and I will say it's fundamental because whenever anybody asks me what I do, and I say I'm an astrophysicist, and they say, well, what do you do as an astrophysicist? I say, oh, I study dark matter. And they say, okay, what is dark matter? And you know you're working on something fundamental when you don't have an answer to the most simple question that somebody can ask, right? So you either know nothing, or you're working on something fundamental. So I like to think of it as the latter. There's opportunity for discovery rather than ignorance. It's a sort of a requisite thing when you give a talk about dark matter that you have some fun pun on the word dark, and so I used a light in the dark. All right. Very good. All right, so I'm going to basically break this talk up into three parts. The first part is going to be how we know that dark matter actually exists in the first place. Why are we considering it? Then things are going to get a little hairy. I'm going to talk a little bit about the theory of dark matter and sort of a motivation for what we actually think dark matter might be and why we think that. And then the third part of the talk will be very sort of up-to-date results that are possibly pointing towards the direction of some understanding. All right, so dark matter can basically be traced back to the father and mother of dark matter. On the left is Fritz Zwicky, and on the right is Vera Rubin. They both made sort of the first. They set up the first key cornerstones of the problem, and showing that there was a problem in the first place. So the first one was Zwicky in 1933. So this is the most famous picture of Zwicky. It's sort of meant to show that he's a very good scientist. He has lots of big books, but you can tell by the look on his face that he was not the most congenial fellow in faculty. And it's true. Apparently it's true he wasn't. I don't think so. Our lives did not overlap, so I never met him in person, but this is what we hear. So in 1933, he was looking at the Coma cluster. This is a picture of the Coma cluster here. Oh, I forgot to mention, of course, interrupt me at any time with any questions, obviously. This is a chalk talk, so I will be using the chalkboard, actually. I don't know, I've never been to a chalk talk, so I don't know if that is usual or not, but from the name, I decided that I would write on the chalkboard some. So 1933, he was observing the Coma cluster. So what is a galaxy cluster? I'm going to write on the chalkboard right now, but I think it's bright enough that you can actually see. It's only going to be a second. So just a brief background here. So we live in the Milky Way, and if we look at the Milky Way from the side, I'm going to draw this picture a lot, but this will be the first time. It looks something like this. There's a disk and a bulge. You're probably more familiar with seeing it face on, where there's a bunch of spiral arms, and the whole thing is rotating around sort of out of the plane of the board. And we're here, right? So just to give you a sort of sense of some of the scales of what's going on here. Okay, so say this is the Earth and this is the Moon. All right, so the distance between the Earth and the Moon is about 250,000 miles. Okay, and then the Earth is orbiting the Sun, which is a distance of about 92 million miles. All right, so now that's a really long time. It takes light, that's a really long, big distance. It takes light 8 minutes to get from the Sun to us. It takes light 1.5 seconds to get from Earth to the Moon. All right, and then, but the distance to the center of the galaxy is 160,000 trillion.
Are there any lights to that blackboard? Pretty dark.
Oh, sorry. You're good. Miles. All right, so that's the distance. This is a dark matter talk. There should be no light in the room.
Could you say that number again then?
Sure. So this is in miles. Sorry.
What is that number?
This is in miles. So the distance from the Earth to the Moon is 250,000 miles. From the Earth to the Sun is 92 million miles. And from us to the center of the galaxy is 160,000 trillion miles. Right. So it's really, really, really long distance. And I'm missing 3 zeros. 1, 2, 3. Yes, I'm missing 3 more zeros. Right. I figured I could give it to you in trillions because the deficit is now in trillions. We understand what a trillion means. Okay, so this is a really big distance, but now this scale of this galaxy cluster is a factor of 10 to 100, even bigger than that, right? So galaxy clusters are about 10 to 100. So galaxies cluster together in groups and clusters. They're actually called clusters. So this is now meant to be a spiral galaxy or something seen edge on. And sort of the distance across these things is sort of 10 to 100-ish galaxy sizes. Galaxies, right? So it's really pretty big. So this is a very large distance. I guess that would be 1.6 to 16 million trillion miles. So it's really pretty big. So what did Zwicky show? Zwicky showed that if you were to look at this picture and estimate the mass of each one of these galaxies, based on how much light they emit, right? Because we have some idea of for a given luminosity, how much mass something has. And you were to say, okay, well, each of these galaxies is pulling on each other through gravitation, so how fast should they be moving, right? As something pulls on something else through gravitation, it speeds it up, it accelerates it. So how fast should these galaxies be moving, given how bright they are, how massive they are? And what he found was the mass that you need is about a factor of 160, I think he said it was, higher than what he saw in the picture. So he said there's missing matter here. More modern estimates put it at a smaller number, but it's still a lot more than the light that we actually see. So he said this was missing matter, and people sort of took him semi-seriously for a while, but mostly said, oh, well, we don't really understand what's going on. 40 years later, yes?
So you're saying that he saw them moving faster than they should be moving?
Correct, okay. Given how much mass he thought they had based on how much light he saw.
Okay.
So 40 years after that, in 1975, Vera Rubin was looking at what's called a velocity profile of a galaxy. So if you look at a galaxy, like this is M31, and as a function of the distance away from the galaxy, so now this is meant to represent the distance from the center of a galaxy, how fast is a star moving? How fast are the stars moving in the galaxy at that particular distance, right? And what she found was that the stars out here at very large distances were moving at the same speed as stars at smaller distances. So basically the whole galaxy was sort of spinning around at some constant speed like this, right? And this is not what you would expect if all of the mass was just in what you see here. You would expect the velocities at higher distances to fall off, that you'd get less velocity at large distance. Okay? But she found that the velocity in fact stayed constant as you went away from the galaxy. And what we now understand is that this galaxy is living in a very large dark matter halo. So there's a bunch of mass on top of this galaxy that we can't see. Right, so those were basically the two key sort of beginnings of the field of dark matter, and it was Zwicky first realizing that these galaxies are moving too fast, and then especially Vera Rubin showing that galaxy rotation curves the galaxies were moving too fast in the outer parts of the stars were moving too fast in the outer parts of galaxies. That really solidified this in people's minds.
When did she make that?
That was 1975. As a historical side note, she was not taken very seriously for a while, likely because of her gender, and her advisor took some of the credit for the work, but eventually it all worked itself out, and these days we know that she's the one.
Can I ask 2 quick questions?
Sure.
The graph that she produced, or that you showed in her picture, shows a spike, and then it levels out to the right. So is that because the mass at the center really is more concentrated, so that's what leads to the dip early on? And then is the fact that it levels out indicate that dark matter is consistently distributed throughout the universe as opposed to being itself clustered like a star or a massive object?
Sure. So the first part is basically yes. In the inner parts of this galaxy, there's way more mass in stars than there is in dark matter.
Invisible matter.
Invisible matter than there is in dark matter. And so the details of this velocity curve depend on the details of the stellar distribution. But at these, there's not enough data to say from this how clumpy the dark matter actually is. We still don't really know that all that well. But what we do know is that the dark matter, there are these large halos that the dark matter sits in. It's not completely uniform in space. There is structure in the dark matter, and the non-dark matter sort of falls into the gravitational well of those dark halos and then starts to form stars and stuff like that. So galaxies sit in these big dark halos. Yeah.
What are your units of velocity there?
Blurry letter over blurry letter. I'm not exactly sure. This plot is merely meant as a qualitative visualization.
Well, is it angular velocity or translational?
Translational velocity. Yes. Okay, and so one of the really big advances was this object right here. Does anybody know what this object is? So this object is called the bullet cluster. The bullet cluster was found in a survey of X-rays. In pink, what you're seeing is X-ray emission. So what the bullet cluster is, it's actually two clusters. There's a cluster here and a cluster here, and what's happened was this one has basically gone right through this one. Well, they've kind of come together, right? So now, what happens when you have a cluster that's filled with galaxies and also gas? Clusters have a lot of gas in them. The gas interacts electromagnetically and it sort of sticks to itself and it heats itself up, and this gas gets very hot in here, right? So now what you would expect, since most of the visible matter is in this gas right here, is what you would expect is if you were to estimate where the matter is in this system, you'd say, okay, there's a big blob of mass right here. So now how can you figure that out? So there's something called gravitational lensing, where if you have a very distant object, like say one of these background galaxies, this is a galaxy behind the bullet cluster, its light is deflected by the gravity of the bullet cluster. And the amount that it's deflected can tell you something about how much mass is in the bullet cluster, right? And so you do that for many, many objects in this field, and you say, okay, well, what does the mass distribution look like? And this is what comes out. Purple is where the matter is. So what happened was these two clusters came together, collided, the gas heated up and stuck to itself, but most of the mass in the system went right through, right?
Oh wait, how do you know that the light was deflected? And that wasn't, are there multiple images of this?
So there's gravitational lensing can be broken up into two categories. One of them is called strong lensing, in which the light actually is broken up into multiple images. And another one's called weak lensing, where an object that is, looks like this gets bent into something that looks like that. And we see these arclets in this image, and you can take sort of these arcs and these shapes to say where the matter is.
So describe again the red and the blue.
So the red is gas, heated up gas. We see it in X-rays. The blue, we don't see at any wavelength. Can't see it with telescopes at all. All we can see is that it's deflecting the light from the background objects. So we know that most of the mass in the system is here and here, but most of the luminous matter in the system is right here. So this tells us two important things. One, dark matter exists because it's deflecting light where we don't see anything, hence it's dark matter. And two, it's what you call collisionless. It goes right through itself, right? So it does not interact via electromagnetic forces. Question?
Is that a blue section up at the middle top?
That right up here?
Yeah.
Yes, it is. So the one of the hardest things to do when you do weak lensing and make maps like this of where the matter is with weak lensing is how to handle the boundary of your box. And it just turns out that mathematically it's difficult to get the boundary exactly right. However, these two blobs are significant at a very high level, but that one up there is not.
Well, I guess a big question is how do you know it's not just non-luminous, that ordinary matter, that it doesn't interact with light at all? I mean, how do you make that leap?
Sure.
Coming later.
That is coming a little bit later, but this shows you right here that it does not interact electromagnetically.
Well, does it? Oh, because
otherwise it would stick to it.
It would have stuck together.
Yes, and heat it up, just like all of this stuff in here, which
the stuff that interacted electromagnetically would stick together.
Yes.
And that didn't.
And well, it would heat up and stick together. Yes, and this stuff did not.
And to heat it up, it would presumably create light.
Yes, exactly.
Doesn't that indicate that the dark matter does clump up?
So the dark matter, so again, this is a cluster scale. So this is the scale that I had on the board over here. So it's a very, very large scale. And so we definitely know that dark matter does clump up on scales that are as big as clusters. We know that it clumps up on scales that are as big as galaxies. Much smaller than that, it starts to get a little fuzzy. No pun intended.
Are you sorry you said we could take questions?
No, absolutely not. Absolutely not. I may not be able to get through everything I wanted to say, but that's okay.
So am I correct that you assume, or have concluded, that the blue clump on the right was associated with the glowing pink to the left? As the two clumps went through one another, the gases were attracted and the blue on the left kept going, blue on the right kept going? That's
right. So this guy is associated with this guy, I believe. So they came through each other, and then these guys sort of slowed down and heated up, and then the dark matter just kept going.
What's the attracting force of the dark matter?
Gravity. So that's, I guess, another thing that this tells us is that it is collisionless in that it doesn't interact electromagnetically, but it does interact gravitationally, which is important. Okay. So what I've told you so far is evidence that dark matter exists, right? We see galaxies moving too fast in clusters. We see stars moving too fast at the outskirts of galaxies. We see gravitational lensing where there's no stuff, right? So we know that dark matter exists. It's sort of beyond a reasonable doubt. So the question is, though, what is it, right? So the next question, I guess, is what is it? That is a very, very difficult question to answer. Well, it's a question which nobody knows the answer. And which will be the subject of what I'm about to talk about. All right, so now those arrows are meant to represent that I'm going to be writing on the blackboards. So this is going to be about sort of the theory of dark matter. So we see these big blobs. What is it made out of? We don't just want to pull our ideas out of thin air. We need to have a model, right? So when you see something in science that you don't understand, you say, okay, well, what could be going on? Let me make a physical model for what's happening, and let me see how well it fits the data. That's science in one sentence. And so that's what we do, and that's what I'll be doing for the rest of the talk. All right, so while I'm writing this down, I'm going to leave up these pictures of evidence for dark matter. All right, so the theory of, I'm going to find a piece of largest chalk. The theory of this stuff is unfortunately filled with a lot of technical jargon, which I will try to keep to a minimum. But if there's anything you want me to say twice or explain more, please just holler. But it is sort of necessary to talk about some of the very recent things that are happening. Okay, so before we talk about what dark matter is, before we hypothesize what it is, let's talk about what it's not. All right, so regular non-dark matter, also known as baryonic, is basically made of the following things. There's protons, which are little subatomic particles that are positively charged. There's electrons, which are particles that weigh 1/1000th of a proton and are negatively charged. And there's neutrons, which weigh about the same as a proton and don't have any charge. All right. So,
The electrons aren't baryons, are they?
no, they're not. Electrons are leptons, yes.
Oh, I was just wondering why
Yeah.
you said baryonic.
So by baryonic here, I mean,
Oh, it means baryons and leptons?
yeah.
Oh, sorry. Didn't
Okay. Well, it means, okay, so in this context, I'm talking about non-dark matter.
Oh, yeah.
Okay? We can even kill the jargon. Non-dark matter. Okay, ready? So us and the building and stars and galaxies are made of basically these things. These things form atoms. So there is the nucleus of an atom, which is filled with protons and neutrons. And these things are bound together. And around the nucleus of an atom are electrons, denoted here by E minus, where the minus is negative charge. Okay? So this is what makes up an atom. This is actually a, without the neutron, it would be a hydrogen atom. But this is an atom with various numbers of electrons and protons and neutrons. You make the whole periodic table. Okay? And now these atoms clump together to make molecules, and molecules make up us and basically everything that we see. There are also other particles that I won't talk about right now. But some words you've probably heard are neutrinos, quarks, which make up these guys, leptons, which include electrons but are other particles as well. And then each of these particles has what's known as an antiparticle. You've probably heard of antimatter. Well, antimatter is just like regular matter, only it has the opposite charge. That's not the whole story because there's an antineutron, which is neutral. So, but
zero.
it has charge minus 0, exactly. So it's not the whole story, but there are also anti-protons, anti-electrons, and antineutrons. And then the anti-electrons are known as positrons. So they're just like electrons, but they have positive charge. So they're called positrons. This is all historical stuff. There's not a whole lot of rhyme or reason to the naming scheme. Okay? So, and this is basically it. Okay, so there's a lot contained in other that I'm not telling you, but this is basically it. This is basically the standard model, what's called the standard model. Standard model of particle physics. It includes things like protons and electrons, miscellaneous other particles, and their opposites. All right? So an important property of the opposites, as you may have heard, is that when an opposite comes together with its non-opposite, when an antiproton hits a proton, they annihilate. They basically explode. A proton and antiproton come in, they hit each other, and nothing comes out but energy. So basically photons, right? That's not entirely true, but for the purposes of this talk, that's basically true. All right. So this is the standard model. So what do we know about dark matter? Well, one thing I can tell you about the standard model is that everything interacts electromagnetically. So the standard model is over there, and dark matter is over here. Dark matter is not in the standard model. There's a box around the standard model, and dark matter is not in that box, so it's not in the standard model. It doesn't interact electromagnetically. So where do we go from there? So the best working hypothesis that we have right now is that the dark matter is also a particle. Yes?
Well, what about the neutrinos?
Neutrinos are in the other over there.
Yeah, but they don't interact.
Very much, maybe that's it.
So the neutrinos, the neutrino masses are too small to be the dark matter, and we know that. And there are some other lines of evidence we have that neutrinos are not the dark matter, but I don't want to get into that right now. But neutrinos are right out, basically. So we measure the mass of neutrinos, and we know roughly how many there are, so we know that they're not the dark matter, because we roughly know how much dark matter there is. So we hypothesize that the dark matter is made of some particle, and we know it's none of those particles. So all particles get symbols and names. This one is called the neutralino. Yeah, I know. Particle physicists can't think of fun names like beach ball or something. It has to be something bizarre like neutralino. And so this is its name, and its symbol is usually this funny-looking X called a chi. So I draw this because I'm going to draw this a fair amount in a bit. So this is what the dark matter is in our hypothesis, and so it has several important characteristics. One, it does not interact electromagnetically.
Can you base that solely on this one picture down here, or is it? I mean, there must be other evidence.
There's other evidence as well. So the cosmic microwave background. If you've heard of the cosmic microwave background, there is strong evidence from the cosmic microwave background that dark matter does not interact electromagnetically. It's a very detailed story. I can get into it later if you'd like. But yes, there is other evidence that it doesn't interact electromagnetically. And certainly not very strongly with electromagnetism, because otherwise it would make photons that we see. Right? 2, it does interact gravitationally through gravity. And so this is stuff that we know we know, okay? So we know this from the bullet cluster, we know this from the CMB, we know this from other observations like galaxy clusters and velocity curves. All right, so that's stuff we know. So now some stuff that we hypothesize. First of all, it is its own antiparticle.
Oh, wow.
This is not like a neutron, where its antiparticle sort of has the same charge, and so it's more than that. It is identically the same as its anti-self. So this has an important consequence, is that when one neutralino comes into contact with another neutralino exactly like it, it self-annihilates.
Oh.
Yes. And so what we talk about is annihilates. Sorry?
And what's the byproduct of the annihilation?
That is number 4. The hypothesis is... So we know what it is now, we can go home. It's dark light, we can't see it. So...
Anti-light, I guess.
Well, the hypothesis is that it quote-unquote talks. People use this terminology in particle physics, but of course it's not actually talking, right? Talks to the standard model.
Greg, is there anything in the standard model that satisfies number 3?
That satisfies number 3. No, there is not. Okay. because there's conservation laws that apply in the Standard Model that don't apply outside of the Standard Model. So what do I mean by talks to the Standard Model? I mean that when two dark matter particles come together and self-annihilate, what comes out of that process is Standard Model particles.
So standard particle molecules have condensed basically out of dark matter, you would say. That was the hidden planetarium people were saying that.
So it's similar. So the idea is, so now this is going to get very abstract, but there is observational evidence to back this up. In the very early universe, very, very early times, there was just a big soup of everything, including standard model particles, non-standard model particles, etc. And as these particles came together, they self-annihilated. They produce standard model particles. Standard model particles. So for any particle physics interaction, you can have the opposite reaction if there's enough energy. So in the early universe where there was a lot of energy, standard model particles would come together and go into non-standard model particles, and it was like a big back and forth thing. And then as the universe cooled off and there wasn't enough energy to go from there to there, it's only now going the other way.
How come in the bullet cluster then they didn't self-annihilate as they passed through each other?
Okay, so now in the bullet cluster, so that's an excellent question. As the bullet cluster, as these two objects went through each other, why didn't they just disappear? And the answer is because the density of dark matter particles is incredibly low. Okay. The number of dark matter particles that would hit each other as they go through here is very, very, very small. Okay.
How do we know that?
So you're all asking questions of the stuff that I crossed out of the talk earlier today. Was like, no, I'm not going to get to that. So how do we know that the density of dark matter particles are low? One of the things that you hypothesize about, actually it's not so much of a hypothesis, you can calculate it, is what is the mass of this particle? And then you take the mass density, so the number per unit volume, the mass per unit volume, and then you say, okay, how many particles do I need to make that mass? And it turns out that the density is so low that they would never hit each other as they went through. So it all has to do with the mass of the particle that you're hypothesizing.
How massive are these guys?
So these guys are, so this is unknown. This is one of the parameters in the model, but they're somewhere between 100 to 1,000 to 10,000 is getting a bit high, times the mass of a proton. So they're really pretty heavy.
They're heavy, but still a lot of them.
All right, so I'm just going to write one more thing on the board before I go back to the projector. And I'm doing not so fantastic on time, but not too bad. So I'm going to draw this process on the board, and it's basically going to be what I refer to for the rest of the time.
Isn't there enough energy in a nuclear reaction to push standard matter particles into antimatter or into dark matter?
Isn't there? I'm sorry.
Energy in the sun to, you said when at the early universe there was enough energy to go in both directions between standard model and
Yes.
dark matter.
Yes.
Isn't there enough energy in a nuclear explosion to cause the same bidirectional interaction?
No.
How about the Hadron Collider?
So that is, I'm going to get to that in 2 seconds. But perhaps. All right, so this is the last thing I'm going to draw. Well, this is the last thing I'm going to draw on the board for this theory of dark matter part, which will end momentarily. So here is basically I won't call it fundamental. This is the interaction of interest for the rest of the talk. You have two dark. So now this is going to be time. And these are two dark matter particles. And they're kind of going like this. And then eventually they hit each other, and something happens in here. We don't know what that is. But they self-annihilate. We do know that from our hypothesis. And then what comes out are standard model particles, positrons and electrons, and maybe a photon. So a photon is just a light ray, right? So now, so this is the interaction of interest that I will try to keep up on the board now for the rest of the time, because this is what you should be thinking about when I show you some of the results that are just coming out within the past year or so. It's an amazingly rapidly evolving field.
But
Okay.
if this energy is so big, then I mean, you could have like dump trucks and stuff coming out of that, couldn't you?
Dump trucks.
Well, I mean,
I'm not sure that the likelihood of going to a dump truck is that high.
what I'm saying is, why not things bigger than electrons?
Sure. So that is all going into this question mark. So these things could be going to things that have more mass than electrons, like protons, for example.
It could be.
So it could happen. Now, in the end, all of these particles decay, all of the heavier particles decay down to the lighter particles. So in the end, you always get the electrons, except for the protons. So except for the protons, in the end, you always get electrons. So there could potentially be a proton coming out here too, but that's inconsequential for what I'm going to talk about. But yes, and in fact, that is something that we worry about a lot when we talk about dark matter models. What happens to the protons? Do protons come out? And if so, how do we observe that?
Does any dark energy come out?
No, dark energy is, as far as we can tell so far, completely non-related to dark matter. And again, this is evidence that comes from the cosmic microwave background. And dark energy is, so I've told you about a hypothesis here, right? So I'm mostly an astrophysicist. I'm an astrophysicist. I'm an astrophysicist, but I have particle physics friends. And when I ask them what the present state of understanding from a particle physics perspective is on dark energy, they either laugh or they just turn around and walk away, because there is no present understanding of what dark energy is from a particle physics perspective. It doesn't fit in any sort of way of thinking right now.
But its aggregate's more massive than the dark matter mass.
It makes up more of the energy density of the universe than dark matter than dark matter does. This changes as a function of time, but today, yeah.
But the ratio is 20 to 80, right?
Ratio between regular matter and dark matter is 15% is regular matter or non-dark matter, and 85% is dark matter.
No, I'm talking about the ratio between dark matter and dark energy.
It's more like 30-70, but yeah, it's very high.
Well, I must have taken my eye off the ball for a moment.
Dark energy has more energy. The energy density of dark matter is higher than matter by a factor of 7 to 3-ish.
Why wouldn't you have dark matter annihilate into dark energy? Somehow the concept seems...
So it doesn't work that way. Dark energy it's not just energy. It's negative pressure, right? So it's pushing the universe apart in the same way that when you push down on a balloon, the pressure goes up, right? This is pushing the universe apart, and so it's sort of like negative pressure. And so they're very unrelated concepts. And there's no way that anybody knows how to relate particle physics, even non-standard model particle physics, to dark energy.
So the theory of everything has a third player.
Possibly. Could be. Dark energy is still so unknown that we don't even know where to place it. We don't even know we can't tie it into the other forces of nature in any way that we can think of. So
Sounds fun.
it is a very interesting problem. We should have a chalk talk here on dark energy.
It's got to exist, right?
Oh yeah. It does exist. The data is pretty strongly in favor of dark energy at this point. Yes.
Dark matter is gravitationally it behaves with gravity.
Yeah.
Why in that bullet cluster, why don't those the dark matter clump together to a high enough density that there would be more interactions than we have? Why is it so dispersed?
So it is clumping together. It's clumping together all the time.
But we've got 14 billion years. Why don't we have some galaxies or stars of dark matter?
There has not been enough time to clump together that much.
They're working on it.
But if it did clump together, wouldn't it self-annihilate, or no?
So the thing to understand here is that this process here, these guys have to be really, really, really close together, right? This is not like a dark matter particle is here and then another dark matter particle is over there. If you have two dark matter particles that are sort of going right at each other, the likelihood of them self-annihilating is remarkably small.
So it takes like Big Bang kind of energies to bring them together, or?
It takes very, very high densities.
But not in stars kind of a thing.
So the
No.
section.
Well, no. In stars, it's a different. So stars do not exist in the center of dark matter potential wells. Galaxies do, but stars do not.
Oh, I guess what I meant was if you had that kind of energy level and density, if it were dark matter, then it would. No. Never mind, forget it.
So I will show you something very interesting about potential of dark matter, about dark matter annihilating in regions of high dark matter density.
So is the cross-section somehow fundamentally different than standard model cross-sections?
The cross-section is different. So as far as we know, there are four fundamental forces of nature: electromagnetism, gravity, the weak force, which has to do with radioactive decay and stuff like that, and the strong force, which holds the nuclei of atoms together. So the hypothesis here is that these guys don't interact electromagnetically, but they do interact via the weak force. And they talk to the standard model via the weak force. In fact, they're called weakly interacting massive particles. WIMPs, exactly. Yes, so that's sort of how they would fit in. And in fact, when I write this question mark here, when I said talks before, what I mean is there's a force that exists in the standard model that these guys also feel, and it's that force that sort of has them talk to the standard model. I know this is a lot of technical jargon, I apologize.
Can we do another seminar on what forces are?
Forces is just something, it's just an object here and how it impacts an object over here.
Next slide.
Next slide. Yes, that's a longer topic. All right.
It's an exercise for the student.
I will leave that as an exercise to the student to show why forces work. If you could show that,
yes,
you would be very famous. But we'll leave it there. Okay, so that was sort of the theory, and in fact, this is sort of the level that most astronomers who work on this operate. So basically, you know almost everything there is to know about dark matter particle physics from the perspective of an astronomer. If you were to get a particle physicist in here to talk to you, they would really beat you with jargon, and but you would know a lot more particle physics. But this is basically all you need to know. All right. So now, when we actually to actually detect these things, of course, as I was saying with science, you make a hypothesis right there, and you say what are the consequences for that hypothesis, and how well does that match data. So people are actively trying to do that, and the detection of dark matter breaks up nicely into sort of three categories. Two of which I'm not going to say anything about. The first is collider experiments, right? So this is a picture of the site of the Large Hadron Collider, which you may have heard about. It's not going to make black holes which eat the Earth, which you also may have heard about. And this is a cartoon of how big it actually is. So, as I was saying, the dark matter particle is in our hypothesis, somewhere between 10 to maybe 10,000 or somewhere in that range, the mass of a proton. And the LHC is sort of just getting up to the energy range where you can start to see the lower end of that. All right, so the LHC gets up to a few thousand times the mass of a proton, but by the time you have everything else happen in your interaction, you can only see things at somewhat lower masses. So they're sort of just pushing, and it's actually really difficult to say. Even if you created a dark matter particle in a collider, it's very difficult to say that what you just saw was a dark matter particle. It's a very detailed problem. It's very hard to address. Then there's something called direct detection. So this is a picture of the CDMS experiment, cryogenic dark matter search. So these things are crystals, and what these guys look for is so here's my cartoon of a crystal. Right, so these are atoms in a crystal, and they're all joined by bonds. Right, so these are atoms in a crystal, and they're bound together. And so this crystal is sitting on Earth, and the Milky Way is in a big dark matter halo. So as the Milky Way, as the sun, which is orbiting the Milky Way, goes through the dark matter halo, WIMPs are coming at us, right? It's just like walking through the air molecules are coming at you, right? And the hope with these guys is that once in a while, a dark matter particle, chi, will hit one of these nuclei, scatter off of it, and then that will make this thing vibrate back and forth. And because it's connected to other atoms in the crystal, they'll vibrate back and forth. And then you have some detector that's on the end that recognizes the vibrations. So you're looking for scattering of WIMPs off of nuclei in crystals.
What about the cross-section question that he asked that I was fumbling at asking? Is there a cross-section issue with that?
So the cross-section for this process? Yeah. So cross-section, we're using this word a lot. So let's actually define it for a moment. So cross-section is how big something looks to something else when they're heading right at each other. So if you imagine two marbles flying at each other, they have to sort of be the distance of a marble apart in order to hit each other. But if you imagine two beach balls flying at each other, they could be a larger distance apart and still hit each other. The size that the thing looks to the oncoming other object is the cross-section. Larger cross-section means that the annihilation in this case, or the scattering in this case, is more likely to happen for larger cross-sections. Smaller cross-sections, less likely. Turns out that the cross-section for this process is not the same cross-section as the cross-section for that process. Yeah, so they're different.
Higher, where is it? Which way is it?
So it only kind of really makes sense to talk about rates. And the nearby, well, it also depends on what crystal you use. So it's dependent on what this object is, right? Whereas if these are two of the same thing, it's you just have one cross section. But here it depends on the crystal. But this process would happen more often nearby than this process. But yes.
Are you talking about germanium crystals?
Yeah.
Okay, down mine shafts.
Yes.
Okay, so we're back to that then.
I noticed a neutrino or something.
Oh yeah. There's a lot of backgrounds in this experiment. Backgrounds is other objects hitting your crystal, and it's a huge, very, very difficult problem to eliminate your backgrounds. It's very hard. Yes.
What is the interaction force there? I mean, it's not the strong force, it's not electromagnetic.
No.
What is causing the interaction between the nucleon?
The weak force again.
The weak force.
Yep. And so you can build, it's called model building, you can build models of WIMPs that have different cross sections for scattering and for annihilation, and then compare those to the data. So the one that I work on mostly is indirect detection. Indirect detection with dark matter is basically a euphemism for astrophysics. So astrophysics is called indirect detection. And I've shown a picture here of a satellite that I'll talk about in a second that has shown some very interesting results recently. So indirect detection is the way I'm going for the rest of the talk for the next 15 or so minutes. All right, so here's the first one. So one thing that you have to understand about this field is that acronyms are essential for success. Everything has an acronym, from WIMP to, well, a payload for antimatter, matter exploration, and light-nuclei astrophysics. So I'm not sure which came first, the acronym or the name. I highly suspect it's the acronym in this case. Somebody wanted to name it after their daughter or something, I suppose, because that shortens to Pamela. And you would say Pamela, but it's an Italian team, so it's Pamela. And it's this guy right here. So Pamela is flying in space, orbiting around the Earth. And what Pamela does is it detects what are known as cosmic ray particles. So these are electrons and protons and neutrons flying through the galaxy, and Pamela is standing up there collecting these things. Electron comes in, Pamela says, an electron just passed by me and it had this energy. Right? So Pamela has a very useful feature in that when it does this, it can tell you whether what just hit it is an electron or a positron. It knows the charge. Okay, so now why is this important? This is important because in this annihilation scenario that I outlined over here, we're looking for these guys. Right? Rather than looking for the dark matter, I guess, directly interacting with matter, we're looking for the indirect byproducts of dark matter annihilation. So we're looking for these guys. So if Pamela can measure electrons and positrons, maybe they have some chance of seeing this signature because it turns out that they're at the right energy range. So this plot on the right here caused a huge ruckus about a year and a half ago. So what this is this is the fraction. So Pamela measures electrons and positrons, and then it gets the total number, sums them all together. It says, how many electrons plus positrons do I have? And then how many positrons do I have? And it takes the ratio of those two, the positron fraction. So of all the electrons and positrons that it collects, what fraction of those are positively charged rather than negatively charged? So now these red dots are what they find. These other points are other experiments that were older. Pamela had higher sensitivity. So this caused a huge ruckus, and the reason is because there's only a couple of ways to accelerate electrons up to very high energies. So what we have here is the positron fraction that I just said as a function of the energy of the particle. Okay? So for reference, 1 here is the mass of a proton. And now we're talking about particles that have the electrons, which are 1,000th the mass of a proton, are now have 100 times the proton's energy because they've been accelerated up to very high energies. There's only a couple of ways to do that. And the dominant way is through supernovae. So supernovae, which Lars can give you a chalk talk about sometime, are exploding stars. You may have given a chalk talk about soon. So supernovae are exploding stars that are very massive, that collapse in on themselves and blow out. And as they do that, they blow stuff out. And that stuff gets accelerated to very, very high energies. In particular, the electrons and the positrons get accelerated to very high energies. Now it turns out that what you expect from supernovae is that the positron fraction would fall with energy. And the reason is because it's harder to accelerate things at higher energies, right? So you get more low energy compared to high energy. All right? Now what you would expect from dark matter, on the other hand, so if your dark matter particle has an energy of 500 GeV, has a mass of 500 GeV, right? E equals mc squared. Energy and mass are sort of the same thing. They're just divide by a factor of c squared or multiply by c squared, and you can go back and forth between the two. So you have something with a mass of 500 GeV. So combined, these things have like a 1,000 GeV of mass, and they annihilate and they produce very energetic electrons. And it turns out what you would expect from dark matter is something that went more like this. And so if you sum up something like this plus something that goes like that, you get this rise in the positron fraction at high energies. So what this plot is telling you is that compared to low energies, there's more positrons at high energy than there are at low energy. And this is not something that you can easily do with supernovae. There are other astrophysical contenders for making this happen, but it's pretty difficult. Regardless, this is one sort of maybe hint that something is going on. And of course, you should never take one thing to be truth. So there are other experiments. Continuing on the acronym chain, there's the Advanced Thin Ionization Calorimeter, which shortens to ATIC, and the Fermi Gamma Ray Space Telescope. So these are pictures of those guys. So ATIC is a detector that was on the bottom of a balloon, and the balloon goes up into very, very high up in the atmosphere, and sort of drifts across a large distance and then falls to the ground, and then you go out and you pick up the payload and you say, okay, what did we find? And Fermi is a satellite that orbits the Earth that was designed to measure gamma rays, make a map of the sky in gamma rays, and I'll get back to that in a second. But both of these experiments can measure electrons and positrons as they come and they hit these experiments. Now the difference between PEMEL is that they can't tell the difference between an electron or a positron. They can only get the total number. All right, and so here's what they found. And now this was like a couple of months later after the PEMEL results, and this was another huge thing. So it's kind of hard to see, but the ATIC guys are these solid-filled blocks, these solid-filled points over here, and the red points are from the Fermi satellite. And again, this is now the total number of electrons and positrons as a function of energy. And here we're going up to a higher energy. The PEMEL energy range stopped right about here. So what ATIC and Fermi are both sort of seeing is, in contrast to what you would expect from supernovae, which is this blue line right here, there's this increase up here at high energies. And again, what you would expect from dark matter would be something that bumps up like this. You would see some excess up here of electrons and positrons due to dark matter annihilation. All right? So this is another experiment that's sort of showing that maybe something is not, oh, thank you, that maybe something is going on, certainly that we don't understand, but that is difficult to make happen with astrophysics alone. But still, not convincing, not 100% convincing. So there is more evidence. So this is the picture that I showed you before. This thing is called the Wilkinson microwave anisotropy probe, which shortens to WMAP. And WMAP is maybe the second most famous satellite that has gone up into space after the Hubble Space Telescope. So WMAP satellite measures the cosmic microwave background. So this is the glow in the universe that's left over after the Big Bang. Right? So WMAP has measured fluctuations in that glow as a function of position on the sky. So it was designed to measure the cosmic microwave background, which is shortened to the CMB. Now that's a whole separate talk. This was a huge, huge discovery, and almost everything we know about cosmology comes from this one experiment right here. It's pretty remarkable. But it also observes the Milky Way, because the Milky Way emits light at frequencies that WMAP observes at. Okay, so now, how is this interesting for dark matter annihilation? So I will write over here now. So I told you earlier that dark matter does make blobs. In particular, galaxies sit at the bottom of potential wells from dark matter halos. So we have another picture of the Milky Way. And it's sitting in some big dark matter halo. And the number of chi particles, the number of dark matter particles, increases as you go towards the center of the halo. So there's lots more chi particles in here than there is out here. And so most of the experiments that I was just talking to you about, so we're sitting here, this is us. So the Attic and Pamela and Fermi and the electrons that they measure are all would be coming from dark matter annihilation sort of within this region right here. But there's a lot of chi particles in the galactic center. So you get more annihilations in the galactic center than you get out here. And so what happens is that you have two chi particles that annihilate somehow, and they make electrons and positrons. But that's not the end of the story, because the galaxy has a magnetic field. Just like the Earth, right? The Earth has a magnetic field which points your compass north when you take out a compass. The galaxy has a big magnetic field too. Turns out that it's really hard to measure what that magnetic field is, and nobody knows, but we do know that it's there, and we have some estimate of how strong it is. So when an electron that's moving comes into contact with the magnetic field, it is deflected from its path. And this is very important, because otherwise we would be fried by electrons, well, heavier particles coming out of the sun all the time. The Earth's magnetic field shields us from a lot of cosmic rays and then creates the aurora and stuff like that. So these electrons, which come out of here, come into contact with some magnetic field line, and what happens is they spiral around. Right? Electrons moving around a field line, by a field line, spiral around the field line. Okay? So now when electrons spiral, they make photons. They emit energy. So as they spiral around, they emit, I suppose it'd be better to draw it this direction, they emit photons called synchrotron. So these are just photons from electrons that are spiraling in a magnetic field. So we see synchrotron at WMAP frequencies, and this is a map of that right here. So I put a big mask in front of the galaxy, but basically we're sitting in the galaxy and looking through the galaxy, and that's this guy right here, and we see all of this emission, this guy up here, this over here, this over here. This is all synchrotron, okay? Now, we have an idea of how much synchrotron we should see from supernovae in our galaxy. And so what we can do is we can sort of subtract that off. And what we're left with is this glowing blob in the center. And this is known as the microwave haze. So these maps are in a paper that a collaborator and I, Doug Finkbeiner, and I published in 2008. So the idea here is that perhaps this synchrotron that we see towards the galactic center, that's not coming from supernovae, is synchrotron coming from electrons that are interacting with the galaxy's magnetic field, and those electrons may be coming from this dark matter annihilation process, which is why it's brighter in the center, where there's more chi particles.
Wait, is the lower one already subtracted, or? So
this is the upper one minus the supernova contribution.
Okay.
So you could say, okay, let me make a model for this dark matter annihilation. What should it look like? It should look something like this. Now I've zoomed into the galactic center. And this is the data. And if you take the data minus the model, it's not perfect, but a lot of this excess that you see is gone. Okay? So the model does a pretty good job of fitting the data. So now again, this is centered on the galactic center because we are in a big dark matter halo, and the density is highest at the galactic center and gets lower as you fall off. Higher density means you have more dark matter particles annihilating. And then the last thing I will talk about. So now this is really new stuff. This was a paper that we just posted to the archive, an online preprint server at the end of the year last year. So now this is the Fermi Gamma Ray Space Telescope, but now using it for what its name says it should be used for, which is measuring gamma rays. So this is what Fermi sees in gamma rays. So now these same electrons and positrons that are here, let's zoom in on this region for a second. So then, if you have an electron that's up here, and let's say just an electron for a second. So in this galactic plane, there's stars, one of which is our sun, but there's lots and lots of them, and they emit photons. And once in a while, those photons hit these electrons. And what can happen then is the electrons can give their energy to the starlight photons and make them very, very energetic. In fact, gamma rays. And so you would expect to see a big blob of gamma rays in the galactic center, as well as synchrotron. This process is called inverse Compton scattering, and you would expect to see a glowing ball of inverse Compton scattered gamma rays right where you see the synchrotron. And in fact, we see something like that once you subtract off other galactic gamma rays from other sources in the galaxy that we know about. So there is a gamma ray haze here that is also seen in the microwave. So this is the gamma ray counterpart to the microwave haze that we also see. Again, both of these, the microwave haze and the gamma ray haze, are both consistent with a dark matter annihilation scenario within the parameters that I outlined as the hypothesis that I said before. All right, and that's the end of the talk. This is the big unknown, and these are some things that may be sort of pointing towards that. So, more questions?
We all know about gravity waves. In fact, we haven't been able to see them. How do they enter into dark matter? Since they're more massive, would they make more gravity waves?
So the answer is yes. Unfortunately, so there's not two dark matter particles coming together. Dark matter particles don't have nearly enough mass to make gravity waves. If they did, other particles would make gravity waves all the time. And the primary source of gravity waves is, it's two compact objects orbiting each other. So much more compact objects are required, and the speeds that dark matter is moving. So the speed with these two things go through each other, I mean, they're moving very fast, but the distances are so big that the gravity waves that you would see have a very long wavelength. So it's difficult to detect dark matter through gravity waves.
What other scenarios do you see on the horizon for other detection methods?
So I'm very optimistic about some of the things that are happening in this route right now, the direct detection stuff. There should be some really interesting experiments coming online within the next couple of years. And now this guy here, there's another experiment that is going to be flown within the next couple of years that will extend this up to higher energy. Now, one of the predictions of this dark matter scenario is that this does not keep going up. It turns over at some point. And what we really want to see is that turnover, and we'll be looking for that. On this front, so this is sort of like, this is hot off the press stuff. This is still work that's ongoing right now. In fact, I have not responded to the referee report for this paper yet. But there it is. So on this front, there's also very exciting things happening. The successor to WMAP, the Planck satellite, was launched in June or July. It's been flying for a while now, and things are pretty well under control. Data is being taken, and a much more detailed map of this will come out of the Planck satellite in a couple of years. So that's pretty exciting.
And that's why Greg's locked up working on this.
That's right. I am a member of the Planck team now, and this is one of the things working. I can't tell you anything. I would not be a member of the Planck team anymore.
With all these question marks, what gave rise to the hypothesis that you emit a positron and an electron in this self-annihilation? Where did that model come from?
So the idea that dark matter particles talking to the standard model somehow is is itself one concept, which I can explain where that came from. But then the standard model particles decay into lighter particles. And so maybe they annihilate to something heavier than electrons, or some other particle that's not electrons, but that particle would always go to electrons in the end. So, but the first part, that dark matter particles talk to the standard model via the weak force. So now, remember I was talking about cross-section? It turns out that if you have this soup in the beginning of the universe where all the particles are being created and destroyed all the time, the number that you're left with at the end, after the universe expands, is directly related to the cross-section, right? Because if you have 100 particles in a box and you let them sit in that box for a year, if you have beach balls in there that disappear every time they hit each other, you're going to have many fewer of them after a year than if you had marbles in there that are hitting each other, right? So the cross-section, after the universe has expanded, the cross-section tells you how many leftover dark matter particles you have. And it turns out that if dark matter does talk to the standard model via the weak force, then the number that you're left over with is exactly the same as the number that we measure with WMAP. And so that's what got people originally thinking that maybe we're on the right track with the weak scale interactions, so the weak force interactions.
Great. I think final question.
From results like WMAP and Fermi, can you extract masses?
Yeah, you absolutely can say for a given mass of a particle and a given cross-section, right? Because the mass tells you how many you have in a given volume, right? Because you know the total density, you know the mass per volume. So if you have the mass of a particle, you know how many you have in that volume. And the cross-section tells you how often that number will hit each other and annihilate to electrons and positrons. And you can sort of play off those two things to give you this and that. And what's interesting is that with the exact same number, you can independently fit this and that and this and that.
Will the turnover on the follow-on tell you about the mass?
Yes. So the mass, since energy is always conserved, you can never create or destroy energy. For two particles that have a given mass, say 100 GeV, they can only make electrons that are 100 GeV or less, right? So wherever this turns over tells you, okay, right here, dark matter particles are annihilating and making everything less energetic than that.
Well, I'd like to say all of our postdocs could do a job as well, but I don't think so.
All right.
Fine job. Thank you, everybody.